Hi guys, welcome back. All right, got one more. Hold on. Well, here we are on the 5th week. Doing pretty good. Oh, give me 1 second. I need to get something for today's lesson. Okay, I'm back. All right, so starting the 5th week, just a quick reminder that we have next exam coming up, the 29th. So it'll be available from 7 to 11:59. So just like the last one. I'll be over chapters 4 through 6. So today's chapter is a little bit long, so we're going to spend time on it today and then finish it up on Thursday. Okay, so don't forget, Mondays I'm here, office hours 1 to 2. Got any questions, feel free to drop by, and if that doesn't work for you time-wise, send me an email and we can arrange for an alternative time. All right, well, let us begin. Okay, got one more here. Yes, Amanda, we're going to be going over chapter 7. Chemical bonding. Okay. Now on Thursday, if you have questions about chapters, we're ahead, which is good. If you have questions about 4 through 6, I do not have problems with spending some time on Thursday, going over some of the questions that you may have. Okay. All right. Otherwise, I will continue with the chapters. All right. So chemical bonding. So here we are. We started off with the elements, talked about the elements, talked about metals losing electrons. Okay. Remember that all metals lose electrons. That's their property. And all nonmetals gain electrons. The ultimate goal is to obtain that octet, those 8 electrons around the outermost shell. So metals, specifically the ones in group 1 and 2A, when they lose those valence electrons, they become isoelectronic as the noble gas behind it, the one preceding it. With respect to nonmetals, excuse me, by gaining electrons, they become isoelectronic with the noble gases in front of them, okay? And the other aspect to remember is by losing electrons, your net charge now is a positive. So those guys are called cations. And I'll be using that term quite a bit, okay? So cations are elements that have lost electrons, which are 99.999% of the time metals, okay? The nonmetals that gain electrons, they have their own name called anions. And they have a negative charge. Now, they each have a different magnitude of charge, positive or negative, and that depends on how many electrons they lose. Group 1 electrons, they will lose one valence electrons, hence have a net positive 1 charge. Group 2 will have a net positive 2 charge, okay? On the other end of the spectrum, group 5 nonmetals will want to gain 8 electrons to get that octet. So they're going to have a negative 3 charge, okay? Negative 3, and so forth. For the rest of group 6, we have negative 2. Group 7, we end up in a negative 1. Now, all these chemicals around us, and there's only 2 types of chemical bonding, okay? Just 2 types. Very straightforward, okay? Now, what I mean by 2 types, let me share this real quick. No, I'm maintaining there. Okay. Ionic bonds. Okay. That is a combination of a metal plus a metal. Excuse me. Non-metal. Sorry about that. And for example, what we put in our French fries, good old-fashioned sodium chloride. Sodium, as you well know, is a metal. Chloride is a non-metal. Okay. Now, when you get a combination of a metal and a non-metal, the bond between them is called a ionic bond. The other one is called covalent. We'll have more to say about this in here in a little bit. Now, that is a combination of a non-metal combined with a non-metal. Okay. And a good example of this would be simply H2O, good old-fashioned water. Okay. You got hydrogen, which is a non-metal, oxygen, which is a non-metal. Okay. Now, the big difference between the two is in the ionic bonds, there is a full charge on the cation and the anion. And so we went over why sodium loses that one valence electron, ends up with a full-fledged positive charge. And we discussed why group 7 elements, nonmetals, want to gain one electron, and they have a full-fledged -1 charge. Now, the bond that they have is really shouldn't be termed a bond, but that's the term they use. Because what it is with ionic bonds, think of them as two magnets coming together. Okay, I got two old-fashioned refrigerator magnets. This is my sodium. Okay, this is my chloride. They attract each other, and that is the bond that they generate. We call that an electrostatic bond. Now, when these non-ionic bonds are put in water, guess what happens? Water breaks them up and they tend to separate. Okay, so if you take sodium chloride, solid sodium chloride, and you dump it in water, it totally breaks it apart to make the ions, you're back to the ions of positive and negative. Now, with respect to covalent bonds, it's a totally different ballgame here. What they're doing is they're actually forming a bond. They are sharing a pair of electrons. And if you're to put them into a water solution, they don't break apart. There's one exception, but when we get to that, I'll explain that one exception. Okay, and I just tell you now, those exceptions are acids. Hydrochloric acid, which is in your stomach right now, is a covalent bond. But because of the property of acids, they tend to break apart, which gives the proton the positive charge hydrogen and the negative charge chloride. But we'll get to that soon enough. Okay, and so the difference is if I were to take pure water and I take some table salt, and before I put the table salt in the water, I put this little instrument. You may have seen it, heard of it, called a conductivity measurement. You put it in there to see if it conducts electricity. Well, pure 100% water will not conduct electricity, so your instrument will be a no current being passed. But I put couple grains of sodium chloride. The sodium chloride dissociates, breaks apart, and now it conducts electricity. Something that's covalent, if I do that, and let's say carbon dioxide. Carbon dioxide is another example of covalent. Carbon dioxide, CO2. If I put carbon dioxide in pure 100% water and measure its conductivity, guess what? It will not conduct electricity, okay? Because when I put a covalent compound in solution, they do not dissociate. They do not break apart, okay? Now, all ionic compounds will break apart and dissociate in water, but there are degrees of dissociation, and we'll get to that too when we start talking about solubility, okay? All right, so just two basic type of compounds or bonds, ionic bonds and covalent bonds. Now, you may want to take that shapes table and download it because we're going to use that quite a bit, okay? All right, so let me clear this out. Okay, so as we just talked about, the goal is to obtain that octet rule, 8 valence electrons. With the exception of hydrogen and helium, they have a separate rule, it's a duet, okay? Because it's the maximum number of electrons that they will, from an energy perspective, be able to handle, okay? Now metals, again, long-term memory, lose electrons and become cations. Okay? Non-metals gain electrons and become anions. Okay, we're going to start putting them together to make compounds and structures. We got a negative and a positive. Now, always remember this. I want to put sufficient a number of positives with sufficient number of negative ions together to give me a zero charge to cancel out. So if I have a compound that has a +1 charge, an ion, and I have a ion with a -1, they come together, 1-to-1 ratio, and you have sodium chloride, for example, okay? But we do have cations that have a positive charge, and we have anions that have a negative charge. So when we put them together, if I have like calcium +2 ion, and I want to combine it with chloride, what does that tell you? I need 2 chlorides because I know each chloride is a -1. So I need to put together 2 chlorides for every magnesium ion to give me magnesium MgCl2, okay? So I want to put them together, and this is where you can actually work with the subscripts. The other aspect is 2 positives do not come together. 2 positives repel. They just repel. 2 negatives don't come together. Okay, they will repel. So it's only a combination of a positive and a negative, a cation and an anion that comes together to form a compound, specifically an ionic compound. Okay, so for ionic examples, we got potassium chloride, potassium K. Remember, chloride is the ion. If it was just Cl2, that would be chlorine. We did talk briefly about the name change when the nonmetals become ions. We had nitrogen become nitride, oxygen became oxide, and fluorine became fluoride. Okay, those kind of things. So we got to start thinking about the names of these because eventually we're going to start naming these compounds. You'll be given a formula like KCl, and it'll say, okay, name that compound. Another example here would be calcium bromide, ClBr2. Now you might wonder, okay, why do I have a subscript 2? Back to what I just stated earlier. We know that the calcium ion being in group 2 has a +2 charge. And now if I'm gonna put it together with a negative or anion that has a -1 charge, I need 2 of them to cancel out the +2 of the chloride. Hence, calcium Br subscript 2 is the structure for calcium bromide. That could have easily have been fluoride, okay, or bromide, chloride or iodide. So you see, we're starting to put compounds together, names. You can do all this mix and matching. You probably have access now to at least 300-400 compounds, any combination that you can put together, okay? That example there, calcium chloride, that could have been fluoride. That could have been oxide, okay? Now, nonmetals, as I stated, they share electrons. Ionic compounds do not share electrons. they just attract each other like two magnets, okay? Whereas in covalent bonds share electrons. Now, in the previous chapter, we talked about electronegativity. When we get more in detail with covalent bonds, this is where electronegativity plays a big role. And that role is what kind of properties those covalent compounds have because of electronegativity. Okay? And some examples are covalent. I just gave you H2O, carbon dioxide, could be carbon monoxide. The main point is it is a combination of two or more non-metal elements. Okay? And that's key to distinguish between the two. Ionic compounds, combination of metal and non-metal. Covalent compounds, combination of non-metals. Okay. Now, here you're asking, why do we write the formula Ca, potassium, excuse me, Br2, not potassium, or calcium, CaBr2? Well, we know that calcium has +2. We know that chloride is a -1, okay? And so when we put them together, we write a subscript to designate it to say we need 2 bromides for every calcium ion. That name would be simply calcium bromide. Now, you can substitute chloride, you can substitute iodide, you can substitute any anion now. Start mixing and matching to come up with a variety of different compounds. Okay. Now, if you see bromide by itself, Br2, then that's the element. But notice how it's written here. It's not bromine by itself. It is calcium written in front of it, okay, followed by Br2, okay. The fact that you got calcium there tells you you have an ionic compound, okay, and not to be mistaken with Br2, the diatomic element, where it's just Br2, nothing around it. All right. So here, you got a list of compounds, and I'm going to go ahead and give you the names. The very first one, K, which we know its name is potassium, okay? Then we see that it's Br, and it's Br all by itself. It's followed by potassium, so that indicates it is ionic compound. Because one, we got a metal, which is potassium, and we have bromide, which is a non-metal, okay? So that one would be ionic. And we could have substituted potassium with sodium or lithium or any other metal, okay? And so that's where you got to go and remember from that periodic table, who are the nonmetals and who are the metals? Because that's going to tell you what type of compound you have here, okay? So the second one is S and oxygen, S being sulfur. Now, sulfur is a nonmetal, oxygen is a nonmetal. Therefore, what I have here is an ionic compound for the second example. Okay, and that, by the way, is called sulfur trioxide. Very nasty smelling gas. Okay, that's the third one, HCl. Okay, that is called hydrochloric acid. And that is the formula for the acid that's right now in your stomach. Okay, hydrochloric acid. Hydrogen's a nonmetal. The Cl is a nonmetal. Therefore, that is a covalent compound. Okay. Then we have Br2, which again, it's one of the diatomic. Remember the 7 diatomic elements. Okay. Being both two bromides, again, both nonmetals. Nonmetals, therefore, are covalent. Then, of course, we got carbon dioxide. Again, carbon is a nonmetal, oxygen is a nonmetal. And then the last entry, we get Mg. And right away, you know that Mg is a metal, and Cl2, which is chloride, is the nonmetal. And so from that list, the only ionic compounds are the first one, potassium bromide, and the last one, which is named magnesium chloride. Okay. And then, like I said, now you can project and extrapolate this information. You see that's chloride, but again, you can do fluoride. That could be iodide, okay, or bromide for these compounds. Now, with respect to ionic compounds, now electrons are totally transferred. Let me it's a little bit closer, better view. They look a little better, more, magnify a little better. Okay. And so we get that purple color sphere. That represents sodium. And then we get the green one, okay, to the left of the arrow. That represents the chloride. Okay. And so the sodium atom has that one valence electron. It will lose that electron, okay, because it's a metal. The chlorine, here's the chlorine, because that's the chlorine atom, will pick up that electron because it has 7 valence electrons. And they come together to create the ionic compound sodium chloride, or good old-fashioned table salt. Now note the size of the diameter of the sodium before and after, okay? Sodium, if you look at the periodic table, is in the 3rd period. So that valence electron is in the 3rd energy level. Well, when it loses that valence electron of 1, guess what happens? Its new radius shrinks because now the new valence shell is in the 2nd energy level. And you can see that when the sodium element, on losing an electron to become a cation, its diameter shrinks, okay? Now, if you look at the chlorine atom before the arrow, the chlorine is going to pick up an electron, okay? Because it has room in that p orbital. It's got the chlorine's in the 3rd energy level, 3p5. So it's got room for one more electron. So when that electron comes in and occupies that p orbital to give you the 3p6 now, okay, it is negative. And so now, instead of 5 electrons in the p orbital, it's got 6. And guess what happens to the diameter of the anion? The anion gets bigger, okay? So when the when we look at the sodium atom, and when it loses an electron, its diameter gets smaller, okay? When we look at the nonmetal, and let me put it up here so you can see it. When we look at the nonmetal, in this case chlorine, and when it gains an electron, its new diameter of the ion gets bigger because it has now an extra electron, which now everybody's repelling now because there's another negative going into the orbital, and negatives repel, so that orbit, that diameter gets bigger. The radius for the anion gets bigger, okay? And they attract to each other because of full positive and the full negative charge, just like the 2 magnet examples I gave you, okay? And then in the far right kind of gives you the structure, the crystalline structure of sodium chloride. Okay, notice the sign piece. Now, consider magnesium and the sulfur atoms. And then we're going to look at the magnesium and the sulfur ions, which is now called sulfide, okay? And so if we look at magnesium, It has 12 protons and 12 electrons. It is in group 2A. Okay, group 2A, so there's 2 valence electrons, plus it's a metal. Therefore, it will lose those 2 electrons. Okay, so now it has 12 protons. It didn't lose any protons, but it lost 2 electrons, and now it has 10 electrons. And so its net charge is now a positive 2. On the other end of the spectrum, for the nonmetal, we have the sulfur atom. It starts off with 6 protons and 16 electrons. Okay, it is in group 6A, and it's a nonmetal, so it wants to gain 2 electrons. And in doing so, now it still has 16 protons, but now it has 18 electrons, giving you an overall -1 charge because there's 16 positives and 18 negatives, okay? So it picked up 2 electrons that magnesium gave up. And now these two can come together to form a compound, specifically an ionic compound. Ionic because we got magnesium, which is a metal, and sulfur, or in this case sulfide, which is a nonmetal. Plus, we can put them together 1 to 1 because magnesium has a +2 and the sulfide has a -2. So we can we can write the formula very simply. We're going to write the formula for this will be simply MgS. Okay, magnesium sulfide. Okay, magnesium sulfide, which is an ionic compound. Okay, because we have a combination of a metal and a nonmetal. Now, if it was oxygen's in the same period. So oxygen also would pick up 2 electrons. We can make magnesium oxide. Okay. Magnesium oxide. We can make that compound too. Okay. So, and if this was, chloride, we can make magnesium chloride, but it'd be 2 chlorides because we know the chlorides each have a -1, so we would need 2 of them. Okay, so to recap the ionic size, cations, when they lose electrons, okay, the outermost shell is lost. The valence shell is lost, but now it has more protons, more positive charge. So they're going to pull those electrons a little bit closer to them, okay? Plus, they lost that outermost shell too. So obviously the cation would be much smaller in diameter than the element they began with. The anions, by picking up electrons, now they got more electrons, 1 electron, 2 electrons, or even 3 electrons, depending on the ion. And therefore, since the negatives repel, they're going to want to push that orbit further away. They repel from each other. Therefore, the diameter of the anion, when compared to the element it started out from, is much bigger. Okay, just like the size. Okay, with that in mind, here's some true and false questions regarding the ionic bonding between aluminum and iodine. It says here that aluminum atom loses electrons and the iodine atom gains electrons. Question is that a true statement?
True.
It's true. 1, aluminum is a metal, okay? And iodine is a nonmetal. So being a metal, they're going to lose electrons. Being a nonmetal, they're going to gain electrons. So that's a true statement. Okay? It says here, the aluminum atom is larger in radius than the aluminum ion. Okay? What would you say? True statement, guys?
False.
False, okay. The aluminum atom is larger in radius than the aluminum ion.
Wouldn't that be true?
True. Now, why would that be true?
Because the aluminum is when it becomes an ion, it's losing electrons and therefore getting smaller, right?
You got it. Okay. The aluminum is a metal. It's going to lose electrons. So aluminum is in group, the third energy level, the third period. And so it's 3s2, 3p1. And so when it loses those 3 electrons, that whole valence shell is now empty. No electrons there. And so now by losing 3 electrons and still maintaining the positive, the 13 positive for protons, it's going to pull what electrons it has even greater. Okay. And so remember, the cation is smaller in diameter than the element that it came from. Okay. Because the aluminum ion is the cation, positive ion. The iodine, the iodine atom is smaller in radius than the iodide ion. Is that a true statement or false? Who wants to take that one?
Would that be false?
Somebody broke up.
Would that be false?
That'd be false. Let's think it through. The iodine atom is smaller in radius than the iodide ion. Okay, so the iodide ion, what did the iodide do? Did it not pick up an electron? It picked up 1 electron. So it's got 1 more electron. And so now in the valence shell, it had 7 to begin with. In the valence shell, now has 8. There's more electrons. Okay? So that's a true statement. And so it's bigger compared to the atom itself, the iodine. And then the aluminum and the iodide ions form a bond by attraction. That would be true. If they use the term atoms instead of ions, that would be a false statement because the atoms wouldn't come together. Okay? It is only the ions that are coming together to form an ionic compound. With respect to metallic bonding, or not much to say about that. It's just that metals on the surface have just a whole bunch of electrons. Okay, and because of that, metals are very good conductors of heat and good conductors of electricity. Okay, they're just flooded with electrons on the surface, and that's all really we're going to say about metallic bonding. There's not much to say about that. Now, when we get to covalent bonding, okay, now we talk about sharing electrons. And there's 3 types of bonds, okay? There's what we call a single bond, a double bond, and a triple bond. Now, we denote that, let me put it here. When we talk about a single bond and you see it drawn, generally we denote it by just a hyphen, okay? Bad looking hyphen, but that's a hyphen, just a line. That line represents a bond between 2 atoms, okay? And in that bond are 2 electrons. Every single bond has 2 electrons, and those 2 electrons are being shared by those 2 atoms that they're bonded with, okay? We also have double bond, and you'll see that denoted by, I'm going to use the equal sign. okay? Where basically I got two lines. And those two lines, each line represents two electrons. So there are 4 electrons in a double bond. Now, I can't draw a triple bond, but essentially it is, 3 lines. Maybe I can, let me draw it a different way. Okay, I will draw it this way. So that would be like 1, 2, 3. Okay, you can see that. Well, imagine that being squared up a lot better than what I did, okay? But 3 lines. Each line represents 2 electrons. So in the triple bond, we would have a total of 6 electrons that are being shared between 2 atoms, okay? So carbon dioxide, for example, here's a formula. We're going to get into how we figure out if it's a single bond, double bond, or triple bond, okay, here in a little bit. But covalent bonding is, here's an example of carbon dioxide, 2 nonmetals, okay? The black sphere in the center represents the carbon in that model that you see, and then the red ones represent the oxygen, okay? And those electrons are being shared between the carbon and the oxygen on each side. If we look at the model of H2O, the red sphere represents the oxygen, with the white ones representing the hydrogens. We call those space-filled models that kind of give us a perspective of what we're looking at, okay? So those electrons are being shared. They're not separated. They don't have a full positive or full negative charge like the ionic compounds. That's important to remember, okay? If I put these into water, they don't dissociate. They don't break up, okay? Like sodium chloride would. They stay intact, okay? The covalent bonds will stay intact. And the only exception is acids. And when we get to that, we'll show you more examples. But for right now, covalent compounds stay intact in a solution, whereas ionic compounds do not. They separate and dissociate. Okay, so single bonds are 2 electrons, double bonds 4 electrons, and triple bonds have a total of 6 electrons. Okay, so that line that I demonstrated earlier, we call that a pair of electrons. So single bond is 1 pair, double bond would be 2 pairs, and the triple bond would be 3 pairs of electrons that are being shared. Every pair having 2 electrons, okay? Now, with respect to energy and strength, the single bonds tend to be the longest. There's a bond, and there's a radius between the 2 atoms that are bonded together. They tend to be longer, and actually the weaker the bonds with respect to energy. The triple bonds tend to be shorter and the strongest, very strong. If you ever seen an acetylene torch used to burn through steel, that's how much energy is there. You get acetylene in the combination of oxygen, you burn the acetylene, a lot of energy is given off, okay? But the single bonds, not so much. A good example of a single bond would be like butane. You got a butane lighter. Yeah, it gets hot, but it can't burn through steel, okay? All right, so with respect to the radius between 2, it was thought that, as in the case of ionic compounds, that once they became ions, they came together, that the radius between the bonds would be the combination of the radius of the ions, okay? And so, for example, you got that R1, which is the black sphere on the left, has X amount of radius, and then it looks like a green sphere, R2, that's the radius for the second element. it was thought that if they come together and then the radius between the two atoms would be the sum of the two radii of each of the atoms. Well, that's not the case. It turns out that if we were to get the sum of, let's say, hydrogen atom and the chlorine atom, then that bond length would be about 0.136. NM is nanometers. That's just a very small measurement. But what it is actually, let me mark that out. It was thought that the radius of the compound hydrochloric acid, HCl, and that's the radius, the bond length between the hydrogen and the chloride would be 0.136 nanometers. Well, it turns out it is actually 0.127 nanometers, much smaller than what was predicted. And basically what's happening is in this area here that I marked with the red circle, there is an overlap, because that is where the electrons are pulling onto each other, and there's an overlap there. So the result being is that when the hydrogen atom and the chlorine atom came together to form HCl, their radius is much less than the sum of the radius of the individual atoms. And that is because instead of coming together like my fingertips representing the radius, there is an overlap between the two because of the sharing of that bond and sharing of that pair of electrons between the hydrogen atom and the chloride atom. Okay. All right. And for a single bond, it's an X amount. For a triple bond, that sharing becomes even stronger, and therefore the radius gets even smaller for a triple bond. So, with respect to energy and bonds, okay, it requires energy to break or form any type of chemical bond. So, breaking a bond always requires E, which is energy. And so, when we write it as a reaction equation, energy is always an reactant, meaning we write it this way, that if we got hydrochloric acid and we put heat into it, we break that bond between the hydrogen and the chlorine, okay, to form the respective hydrogen atom and the chlorine atom. Takes heat. That, what we observe is that reaction actually, let me change this a little bit. That reaction actually gets cold because it takes energy from the environment, and we call that endothermic, an endothermic reaction, okay? You might be familiar with this. For example, if you go to the pharmacy to buy a cold pack, you take it and there's a little package of chemicals inside. You take it and you break it up. After a while, it gets cold. That's a cold pack. That is an example of an endothermic reaction because it takes energy from the environment, resulting of it being cold. So to break a bond, it requires energy. And here we say heat because that is what's giving the energy to that bond to be broken. When we form bonds, it always releases energy. We call that exothermic. Okay? Exothermic because energy is given off. And again, a classic example of that would be going back to the pharmacy again and buying a hot pack. You buy a hot pack, again, there's chemicals in the package, smack it, break that package inside within the package, it gets warm after a couple minutes, okay? And it's because that reaction in there, that's occurring in the package is giving off energy, and we call that exothermic. One way to remember this, think of X as exiting the building. So heat is exiting from the two reactants. And therefore, when we write a reaction formula, we have H to the left of the arrow. Here's our arrow. Here's our arrow right here, okay? To the left are the reactants, to the right are the products, okay? And therefore, being exothermic, heat or energy is a product. Okay? It releases energy. Up in the first example, heat is a reactant, okay? It requires heat to break that bond. Break that bond. All right, so let me clear here. So here we have hydrogen sulfide, another nasty smelling gas, H2S. So question here, true or false? Electrons are shared in H2S. What would you say?
I'm going to guess true.
Yeah, that's true, but you don't have to guess, okay? Look at the formula, look at the atoms. You got hydrogen, you got sulfur. Okay, is there any metal involved there?
No.
No, exactly. Therefore, it's covalent. It's a covalent compound. Therefore, all electrons are shared in a covalent compound. Okay? If that would have been sodium chloride, the answer would have been, well, the answer would be false because it's ionic and the electrons are not shared in ionic compound. So that is a true statement because that particular compound is a covalent compound made up of nonmetals. Same would be true for H2O, water, carbon dioxide, anything that is two nonmetals. The bond between H and S is ionic, based on what I just stated. Would that be true or false?
True.
Mm,
No,
False.
that'd be false.
That'll be false. Why would it be false?
Because they're both gases. They're non-metal.
They're non-metal, not gases. They're non-metal, okay? They're both non-metals, so that's a false statement, okay? The bond length, there's a bond, okay? That hyphen between the H and the S represents a electron bond, one pair. One hyphen represents one pair. The bond length is less than the sum of the two atomic radii.
That would be true.
That'd be a true statement because again, there's overlap. They don't come together like the end tips of my fingertips. Some of the fingertips get overlapped because they're sharing those two electrons. Okay. Now, when we get to electron negativity, we're going to find out that that sharing could be either equal sharing or unequal sharing. But for right now, we're just going to call it sharing. Okay. Breaking that HS bond releases energy. Would that be a true statement or a false statement?
Would it be false?
Would it be false? That'd be correct. Because to break any bond, to break anything, it takes energy. You got to put energy into the system to break that bond. Okay. All right. So we're going to slowly get into how we're going to come up with structures, okay, and how things are put together. And that is why the shapes table, if you don't have it, let me Give me 1 second. Let me pull it up here real quick. No. Where'd it go? Okay. The shapes table is going to have this table here. Okay. Now, we're going to use this quite a bit. Let me zoom up a little bit. Okay, because based on what we're going to start talking about, we're going to take that information and then use this table to tell us the shape of that compound. And these are the relative shapes that we'll be working with. Okay. So if you haven't downloaded this and printed it out, you might want to, because we'll be using this quite a bit. Now, if you look at the far left column, that is called a general formula. Okay, label for general formula. Any compound that we work with, you're always going to have a central atom. And we will tell you who that central atom is. That central atom is denoted in the general formula as A. Okay. And again, I repeat, A and B it's a general formula. We're not talking about any specific element, just very general formula here. So A always is the central atom. B represents how many atoms are bonded to the central atom. So in that first example, we have a subscript B, 2B. That means that we have a central atom with 2 atoms bonded to the central atom. B can be the same element or they could be different. Doesn't make a difference, okay? B, I repeat that. B can be the same or different atom or element. Sometimes there's 2 of them, sometimes there's 3. If I scroll down, sometimes there's 4. Now on the central atom, this will become clear as we do an example. There could be a lone pair of electrons denoted by that little diagram in that column in the next column over. You see those 2 little dots? Those represent 2 electrons on the central atom. Okay? There's only, in this case, there's only 1 pair of central atoms. They're not bonded to anything. They're just lone pair that occupy the central atom. Sometimes we have 1, denoted by that example here. Okay? Sometimes we have 2 of them, but denoted by the bottom example. And let me highlight that. If we look at this formula here, we see the central atom is right here. That's the central atom. And that is represented by A. It has 2 atoms bonded to the central atom, which are represented here and here. But it also has 2 lone pairs of electrons on the central atom, okay, which are denoted by the subscript E. Now, this table only is specific for the central atom. What happens to the rest of the molecule is not important, only to the central atom. Once we, let me clear it up a little bit. Once we determine the general formula, it would give us the molecular geometry of that compound. And that molecular geometry has a specific name, which is the name of the shape. It could be linear, which is the first example. And then we have a bond angle, which represents that bond angle between the beads. So we got here something that's linear. There's 180 degrees in that bond angle. Something that's trigonoplanar has 120 degrees. That's what that arc represents, is that bond angle between the B's. Okay? The most standard bond angle that nature has is the next one, tetrahedral, 109.5. That is the maximum angle that, remember that well, let me point to it. These lines right there and right there, okay, those are bonds. Those represent bonds. Those are electrons. There's two of them in each line. And being negative charge, they want to repel from other bonds. So this is the optimum configuration when you have 4 bonds in the central atom that molecule occupies, because those electrons want to repel as far away from each other as possible. So tetrahedral tends to be the most common configuration of nature that we have. Now what happens is when we put a lone pair on the central atom, those 2 electrons are not bonded. We call that lone pair. They're not bonded. They occupy the central atom, but they tend to occupy a lot of space. So they have 2 electrons in that lone pair lobe there, and they repel each other. Guess what? It results in this bond angle to shrink. That's why we say less than 128 degrees, because the lone pair occupy more space, causing that bond angle to shrink in. And that bond angle is designated as less than 120 degrees. Okay. And if you, let's scroll this down. Oh, come on. If we have 2 lone pairs, okay, they occupy a heck of a lot more space, the lone pair, causing that angle to be much, much less than 109.5. So that is what is meant by the bond angle. Okay, so we're going to be able to be in a position, once we go through some examples, of being able to, 1, come up with a general formula for the compound, and from that general formula, be able to determine the geometry, the name of the shape, and the bond angle appropriate for that particular general formula. Okay? And it's all based on valence electrons. And so it's important to take or remember how to calculate or determine the number of valence electrons from the periodic table. Okay, so but before we begin with that, we know how many valence electrons. If you don't know, you go back and refresh your memory on how to obtain the number of valence electrons, because we're going to use what's called the Lewis dot structures to designate the valence electrons. And it's pretty straightforward. We find the group number that tells us how many valence electrons, okay? And then find the atom and then put a dot to represent the number of valence electrons for that particular element. For example, potassium. Potassium is in group 1, has 1 valence electron, right? Oxygen's in group 6, has 6 valence electrons. Silicon's in group 4, 4 valence electrons. Magnesium's in group 2, 2 valence electrons. And iodine is in group 7, 7 valence electrons. Therefore, to draw the Lewis dot structures, that's all we got to do. Each dot represents the valence electrons. So potassium's in group 1, 1 dot. That is a Lewis dot structure for potassium. That is a Lewis dot structure for oxygen, because it's in group, has 6 valence electrons, okay? And silicon has 4 valence electrons. Magnesium has 2 valence electrons, and iodine has 7 valence electrons. All right, so which that is the Lewis dot structure for atoms. Pretty straightforward. But now we're going to get into the Lewis dot structures for compounds. And what we do first is we add up the total number of valence electrons that every atom brings to the table or brings to the structure. Okay? Now, then you'll be given the central atom. You'll be told who's the central atom. And that means that all of the other atoms that are involved are bonded to the central atom. Okay? So either central atom will be underlined or be in bold. Okay? And then the thing to remember is the octet rule. When we add up all the valence electrons, that is the number that you have to work with. Okay? You can't arbitrarily either take valence electrons out or add them in. If you have 8 valence electrons, and that's what you work with. And you adjust them and put them on the structure such that the octet is fulfilled around all the atoms, except the most obvious is hydrogen, because hydrogen has a duet rule. So hydrogen only needs 2 electrons around it. Okay? Everybody else, we have to adjust the valence electrons that we have to work with in such a manner that the octet is fulfilled. Okay? Then we check, double check, go back and count, make sure we still have the same number of valence electrons that we did in step 1. And then identify which ones are bonded and which ones are lone pairs. Remember, lone pairs are atoms that are on the central atom that are not bonded to anything, and they're just sitting there, 2 dots sitting there in the central atom. Okay? Now, once you put the formulas together, and like I said, you try to put them in such a manner that the octet's fulfilled, well, sometimes you can't do that. So what happens is you start creating, start making double bonds or triple bonds. And I have an example to show you here in a bit. So you make double bonds and triple bonds to share so that the octet is fulfilled amongst all the atoms. Okay? Okay, so for example, let's do H2O, water. So we add up the valence electrons. Now we know hydrogen brings in 1 valence electron, but there's 2. Don't forget to count the number of atoms that you have of each one. So it's 2 times 1. Then we look up oxygen. Oxygen is in group 6, so it brings in 6 valence electrons. We don't care about the core electrons. Remember, all the action happens on the outermost shell. That is where all the chemistry occurs. The innermost shells, the core electrons, they're full. They're not going to be very favorable to form bonds, okay? Okay, so we have a total of 8 valence electrons between the 2 hydrogens and the oxygen. The oxygen is the central atom, okay? And so we can put a bond, put oxygen there, and just put a line for a bond between the hydrogen and the oxygen. So let me do it this way. I put a text here. Now, there are 8 valence electrons from that. What I like to do is I just divide it by 2. And that tells me that I got 4 pair to work with. Okay? Because later down the road, I'm just going to draw a line or a double line. Okay? And by drawing a hyphen or a line, 2 lines, each one represents a pair. So I got 4 pair to work with. And now with 8 electrons, that's not a lot, but you could have up to 32. And sometimes it's easier just divided by 2, and you say, I got 6 pairs, keeping in mind there's 2 electrons per pair, okay? And so I got 4 pairs to work with. So I know that oxygen is a central atom, so I have the hydrogen I can draw, and then I can draw a bond between the hydrogen and the oxygen on one side, and then the other side I can draw a bond between the other hydrogen and the oxygen, okay? Now that takes care of 2 pairs, right? Because I have a pair that I use for each hydrogen. And so, 4 minus 2, I got 2 pairs left to work with. Now, I got to put them someplace. I can't put them on the hydrogen because the duet for hydrogen has been fulfilled. So the most logical place has to be oxygen, okay? Because we need that octet. And so we put, let me see if I can draw this. Let me separate. Okay. Let me separate there. So that's the formula I wrote that took care of 2 pair. I got 2 pair to work with. Okay. And so I got to put them someplace, and I can't put in my hydrogen because hydrogen, the duet is full. You see that line is a shared pair of electrons that is shared between the hydrogen and the oxygen and counts. And if I count them, there's that 2 electrons are shared to the oxygen. So oxygen has it for a period of time, and hydrogen has it for a period of time. They're sharing, okay? The other 2 pairs, the only thing I can do is to draw me a line on the central atom, okay? Now, when I count the total number of electrons that I have, I got 4 lines there. I got the 2 red ones, that's 2, 4, 6, 8. Those are 8 electrons, which is what I calculated up here with respect to the valence electrons. Since there are lines, that represents a pair. Isn't that 4 pair? Certainly is, because I just took my 8 number. I'm always going to have an even number. I'm always going to have a number divisible by 2. So I got 4 pairs that I calculated. I got 4 pairs, okay? Of those 4 pairs, 2 of them are bonded to the hydrogen, and the other 2 are not bonded to anything. Those are what we call lone pair. They're just sitting on the central atom, okay? And so from a general formula, when I look at the structure I just wrote, A is always there. A represents the central atom, which is oxygen, right? B represents whatever's bonded to the central atom. Well, how many atoms are bonded to the central atom? How many? You can tell me. How many atoms are bonded to the central oxygen?
2.
2.
Exactly, 2. So it's AB subscript 2. Now, I also have the lone pair. Now, how many lone pair do I have?
2
2.
pairs.
Exactly, 2. So that's my general formula, okay? Based on the valence electrons I started off with, how I put the structure together, which gives me the general formula. This is just a general formula that I'm going to use to go back to the shapes table. Keep in mind, it's AB2E2 is my general formula. Therefore, I go to the shapes table. And do I have anything that matches that? Sure enough, look at that right here. AB2E2. So that is the geometry and its name is called bent, and its bond angle is less than 109.5. Okay? So that's how we use the shape table based on the valence electrons to give us the formula. So let us go back. Okay. And so this rehash of what we just went through is right there. You have the two lone pairs sitting there on the central atom, okay? And keep in mind that the line represents a pair, which is being shared. So when I start counting the octet, okay, I simply just look at the central atom by itself, just looking at the oxygen. I have 2, 4, 6, 8 electrons around the oxygen. Because those in the line are being shared by 2 atoms and therefore can be counted individually to each atom. If I look at just hydrogen by itself, okay, it's got 2 electrons around it, okay? So the octet for the oxygen has been fulfilled. There's 8 valence electrons around it, oxygen. 2 pair are lone pairs, they're not bonded, and 2 pair are bonded, okay? And if we look at the other hydrogen, okay, you can see there's that line is being shared between the oxygen. So the duet has been fulfilled for hydrogen too. Okay, those lone pair only pertains to the central atom. They have nothing to do with the hydrogens. All right, let's do a couple here. All right, I'm gonna give you the formulas here. Then I'm gonna do one example, but try these at home. Okay, now I'm gonna run through the HCN. Okay, the first one is the central atom there is given to you, it's underscore. So HCN, which hydrosonic acid, it's comes from from cyanide, but this is poisonous gas. Anyways, HCN, carbon's the central atom. Okay, the next one is the fluorohydrocarbon. Carbon again is a central atom. That means the hydrogen and 3 fluorides are bonded around. Carbon dioxide, central atom, 2 oxygens bonded around. And then the last one is NH3, which is the formula for ammonia, by the way, if you want to know. Oh, then I got a question. Oh, 3-minute warning. Thank you. Yeah. Well, let me quickly go and do the HCN, and then we'll stop it there. All right. So HCN, hopefully you can see that, the front center. Carbon is the central atom. Okay. I just put this together, so it may not be in the PowerPoint slides that you have. Okay, I add up the valence electrons from every atom. Okay, so that means hydrogen brings in 1, carbon brings in 4, and nitrogen brings in 5. So I have a total of 10 valence electrons, or 5 pair. Okay, so you took the 10, I just divided by 2. Remember, I always end up in the even number. If you don't have a number divisible by 2, and check your valence electrons. Make sure you got the right number. Okay. Since carbon is the central atom, I can very quickly bond hydrogen and nitrogen to it. So that hyphen, that bond is, I got hydrogen, hyphen, carbon, hyphen, nitrogen. Okay. That takes care of 2 pairs. So I got 3 pair to work with now. I got to put them someplace. Obviously, I can't put them on the hydrogen because their hydrogen is already full with a duet. So I can put them anywhere on the carbon and the nitrogen. Where you want to put them is totally up to you. Okay? All right, so I end up with that. You see what I got here? Let me see if let me highlight that. I end up with this. I was able to draw in. Do I still have 5 pair there? Okay, I still have 5 lines. There's 5 pair. In my case here, I just put the 3 other pair around the nitrogen. I could have put 2 pair in the carbon and 1 in the nitrogen. Doesn't make a difference. But I can't put them on the hydrogen because the hydrogen's already full. Okay. Now I check my octet. If I just look at nitrogen by itself, right there, I see that I have 2, 4, 6, 8 around it. Do I not? Yeah. Okay, let me clear it so we can get the carbon. Now look at the carbon by itself. Carbon only has 4. 1 pair is shared with the nitrogen, 1 pair with the hydrogen. Okay? And so the octet is for the nitrogen is good, but the octet is not good for the carbon. And so what I do here is I borrow from Peter to give to Paul. Okay? And so what I do is I take a pair that I put a nitrogen right here, and I make a double bond. Okay? And it looks like I'm going to have to make 2 double bonds. Okay? And in doing that, I got the formula there. Okay? Now check the octet. Looking at nitrogen by itself, I have 8 electrons around nitrogen. I got 3 that are bonded and 1 lone pair of nitrogen. And if I look at carbon by itself, I have 2, 4, 6, 8 electrons around carbon. Okay? Now, count overall, do I still have 5 pair? Sure enough, 5 pair. You remember, you can only work with the pair that you have. You cannot arbitrarily just add electrons or take them out. All right, sorry I took off too much of your time here. I went over a couple minutes, but we'll continue with this on Thursday. We'll knock it out. We're about a little bit less than halfway through. So let me pause here, stop here. All right.